Hello Math 4411 students, let's begin lesson 6, Cosets and Lagrange theorem. The main tool for lesson 6 is the theory of equivalence relations. So if you're unsure of any of these, equivalence relations, equivalence classes, equivalence partitions and quotient sets, those kind of things, then please review section 0 of this notebook. Also, you may want to take some time on modular equivalence, the construction of ZM as well. Otherwise, let's go to section 1, cosets. Let G be a group and let H be its subgroup. Then we define the relations, the left coset relation and the right coset relation like this. A inverse B belongs to H versus AB inverse belongs to H. So the inverse comes to the left or the right. That makes the difference. We claim that this is an equivalence relation and we're going to study their equivalence classes. Of course, we have to prove it. We have to prove these: the reflexivity, symmetry, and transitivity. Let's see, is this true? The reflexivity. Is this true? Well, the definition goes like this, so we can rewrite this. And then what do you think? Is this true? Yes, of course. A inverse A is the identity E, and that always belongs to any subgroup. So the answer is clearly yes, and here's the proof. It's a one-liner. Now how about the symmetry? If A belongs to B, then B belongs to A. That's something we have to prove. Is this true? Well, the definition of A belongs to B is right here. So, okay, let's rewrite that. Then, is this true? Up to switching A and B. What do you think? Is this true? How do you prove that? Well, please make this observation. A inverse B inverse is actually B inverse A. Remember the inverse formula of a product? Distribute the inverse to each element, but in reverse order. So B inverse and A inverse and inverse again, we get A back. So the other element is actually the inverse of this, and H is subgroup. So yes, it belongs to H as well. Okay, that was another one-liner. And then how about the transitivity? Maybe that's a little bit more complicated. And B belongs to C. And A is related to C. Okay, that's the transitivity, isn't it? A is related to B and B is related to C, then A is related to C. Let's rewrite this in terms of the definition of the left coset. So A is related to B means this, isn't it? And then B is related to C. That means, and then we have to prove that A is related to C. Okay, how do I prove that? Looks like that's pretty simple as well. All we have to do is multiply these two. A inverse times B inverse times C. Then these two will just kill each other off because we got identity. So you just get A inverse C, and yeah, that belongs to H because H is a subgroup. Here's a full proof. The key idea, that one just drops out, and then we have a product of two members of H, and H is a subgroup, so yes, it belongs to H. So that's the proof for the left coset relation, and the right coset relation, well, that'll be students. That'll be left to the students. So we'll assume that we proved for everything. Both the left coset relation and the right coset relation are equivalence relations. Consequently, we can consider equivalent classes, which we were going to call the left coset and right coset. They look like this. The equivalence class for left coset relation looked like this. Turns out it is a set of A times some member of H form, which we call the left coset. Multiplication is to the left-hand side of capital H. And the other way around, the multiplication is now to the right-hand side of capital H, HA form, where H is a member of capital H. And those form the equivalence classes of the right coset relation. Basically, we have to prove this. You see, A is related to B, which is, of course, this by the definition. That means B belongs to equivalence class of A. So proving this equivalence here, which I just highlighted in red, will prove that this set, AH, is the equivalent class. So the set of all elements that are related to A. So related to A, if and only if B is A times some H form. So how do you prove that? So A is related to B is, of course, okay, it's a little bit hard to rewrite. That's equivalent to that. Okay. And that's equivalent to A inverse times B is some H. Oops, small h. Okay, that's what I intended. Is that clear to you? That's the definition. And then A inverse B belongs to H means A inverse B is some small h which belongs to capital H. It's just a trivial way to rewrite this, but this expression really helps because now that we have equality, I can do some algebra, multiply A to both left-hand side and right-hand side, and flip it over. You see, I can do this now. Multiply A, so that they move out, they become E. So B is AH. And now B is A times certain element of capital H form. So we can say B belongs to AH. So rewriting this belongs to capital H as equal to some small h that belongs to capital H. Rewriting like that we can do all kind of algebraic manipulations. It's a typical trick, actually. Whenever you have to use some algebraic operations with inclusion, we have to deal with a lot of inclusion problems in analysis as well, but that one's totally different. But in algebra, this is very, very typical. By the way, here's a full proof. Okay, this is a proof for the left coset relation, and the proof for the right coset relation is left to the students. This one, I'm not going to do that. It's pretty much the same, so I'll leave you to do those. So what do we have? The left coset and the right coset are the equivalence classes of the left coset relation and the right coset relation, respectively. So those are equivalent classes, and entire group G can be decomposed by equivalence classes, which form equivalence partition, and they're all unique. And then we can do some more math about those set of equivalent classes, which we call the quotient set. And does it also have the group structure with respect to some algebraic operation induced from the original? Under what circumstance? Oh, we have to consider a lot of things. But for now, let's be satisfied with just construction of this left coset and right coset from the left coset relation and right coset relation. One final note: if G is abelian, then the left coset and the right coset are the same, because basically there's no difference, because you see multiplication is commutative, so A times H versus H times A, they're the same. But in general, when your group is non-abelian, then they may be different. Even when they are non-abelian, if they satisfy this particular property, then it turns out to be okay. The left-hand side and right side coset are the same. And this kind of subgroups are called normal subgroups. And for abelian groups, every subgroup is normal, but for non-abelian groups, that's not always the case. Let us solidify our understanding through a couple of examples, but I don't know whether we'll have enough time for... No, I'd rather stop here and let's consider examples in separate videos. Maybe one, maybe two. We'll do those in separate videos. See you soon.